everyone. So this is going to be the last part in the Newton's three law videos. This is all about Newton's third law. Again, this is going to be another one, much like the first law, that you've all probably said and heard at some point, but we're going to actually explain it in a little bit more detail. So once again, the first law talked about why objects move. The second law kind of talked about how they moved, relative force and acceleration. This one, it's more about what happens to the motion when objects are interacting. Like, how do objects kind of interact with each other during these motions? So, a good example is imagine a man's on a on a skateboard and throws a basketball forward towards a friend. Does the man stay still or will he end up moving? And if so, what direction? So if you've ever done this before, gone on skates or on ice skates, rollerblades, or a skateboard, and you've ever thrown something at someone else, you may have noticed what your body will do as a reaction. The third law states for every action, there is an equal and opposite reaction. So when the man on the skateboard throws the ball forward, what's actually happening is that he is being pushed backwards and he'll actually move backwards relative to the ball. You can try this out yourself. Typically, you want to make sure that the thing that you throw is relatively heavy compared to you. If you throw a small paper ball, you may not see this reaction, but if you throw something really heavy, you'll see your body actually get pushed backwards. And the heavier the object, the greater the pushback. Now, this law is basically the law of action reaction pairs. That anytime we have objects interacting, there's always going to be this force symmetry between them. That when you push on something one way, that thing pushes back on you the same way. When I put my hand on the wall and I'm pushing into the wall, because I'm not moving forward, the wall has to be pushing me backwards with the exact same force. Walking is another example. When you walk, you may not think about it this way, but when you're walking, you are actually physically pushing backwards on the ground so that the ground pushes you forward. Swimming is another example. When you are swimming, you are literally taking the water and pushing the water backwards, and that push backwards propels you forwards. For the most part, you can attribute any type of motion based off of this action reaction setup. Yeah, so a common joke that I always say is that like you can get away with the comment of when you hit someone claiming that they technically hit you back. If you punch someone in the face, you technically can argue that that face actually hit you back with the exact same force. One of the stories I always like to tell with this is the story of my dumb friend Steve, one of my best friends in high school, though, as the name implies, very dumb. He is a perfect example of this law. One day we're in a garage playing ping pong, and he got really upset because his brother was beating him. His younger brother was beating him, and so he, in a fit of rage, decides to punch the wall of the garage. When he did that, he happened to hit the stud of the wall. For those who don't know what a stud is, that's where the thick wood beams are that are actually supporting the walls and holding up the walls in place. So his hand went into a typically very sturdy piece of wood, and because he hit it with as much force as he could, being a very strong guy, that wall hit him back with the same force, and he ended up breaking his hand. So this is the whole idea of action reaction. When you punch something, that thing punches you back, causing you pain. If you want to move forward, you have to push something backwards. Now, the one way that you can kind of identify these questions is that the wording is really weird. You kind of have to almost read it a few times just to kind of get an idea of what it's asking, because it almost sounds like it's saying the same thing, and that's the whole point. It is the same thing. So this is a very good example. Uh, if the force that A exerts on B is 8 newtons, then what is the force that B exerts on A? Like I said, it may take a few times reading that to realize that, oh, they're switching the B and the A. But for the most part, it does look like it's the same statement. Um, so the answer will always be the same. It doesn't matter the setup. If you exert a force on something, even if that object is smaller, it doesn't matter. It exerts the same force on you. Now we talked about how the Earth pulls us down with gravity. That's what we call the weight of us. If you're 150 pounds, what that essentially means is that the Earth is pulling you downwards with a force of 150 pounds. But according to Newton's third law, that also means that you are pulling the earth up with a force of 150 pounds. Now, it's not noticeable because of the fact that, again, it's all about inertia, Newton's first law. Because the earth has so much more mass, it has so much more inertia, that amount of force is not enough for an effect to be noticeable. But on something like us, much smaller, much lighter mass, it is much more noticeable. But yeah, the main idea is try not to read into these questions too much. You see these things of this exerts a force on blank. What about when we flip it? The force is always the same. In fact, I mentioned before that one of the questions that the smartest kid had gotten wrong was the math question. This is the other question that he was getting wrong, was something very similar to this. So these are just all examples. Again, rockets are propelled using this idea of the third law. They expel gas out one way in order to propel themselves forwards. If you want to push something forwards, you are actually pushing with your feet backwards. You can try this if you want, where you get two people either on ice skates, rollerblades, or skateboards. You push one, and you'll notice that it will actually push you backwards with the same force. You may not feel the same effect, but you get the same force. Now, this is actually something that's really important to point out. The forces that both people experience will be the same. The effect, however, may not. When a bus is driving down the road and it hits into a bug, both the bus and the bug are feeling the exact same force. But because the bus has a much greater inertia and a greater mass, it feels a much smaller acceleration during this collision, while the bug, being so much less mass, will feel such a high acceleration it will literally explode during the collision. We can actually see it in the equation F net equals ma. So since the bug and the bus feel the exact same force, there is an what we call an inverse relationship between mass and acceleration, meaning as one gets bigger, the other has to go smaller in order to maintain this same level of force. If you are increasing the acceleration an object is feeling with the same force, that means the mass has to be decreasing, and vice versa. If you start increasing the mass on something without changing the force, then the acceleration has to be going down. This is what an inverse relationship is. As one goes up, the other one goes down. Um, do not confuse this with indirect. There's really no such thing as an indirect relationship. It's only inverse and direct relationships. Um, yeah. So this is a bunch of the same stuff about how movement is pretty much all about this Newton's law. Oh, baseball is another example. If you've ever hit a ball, some of you may have noticed that there's kind of like a reverberation in the bat, and you almost feel your hand stinging. It's because of the same idea that when you hit the ball with the bat, technically the ball hits the bat with the exact same force, and that's kind of what you're feeling. Guns are a perfect example of this. Unfortunately, these animations aren't really working, but you should be able to get the gist that, if you've ever seen a gun being shot and how it kicks back, it's all again about the Newton's third law that the gun shoots a bullet forward, the bullet shoots the gun backwards. I know it sounds weird to think of the bullet shooting the gun, but it's just supposed to represent the idea that they're feeling the same effects. One is being pushed forwards, one being pushed backwards with the same force. But because the bullet is so much lighter, it's going to come out of the gun at such a fast speed, while the gun kind of gets a slight kickback, compared to the bullet. In fact, thankfully, the gun doesn't shoot back with the exact same velocity, or else uh, a gunshot would pretty much be an instant kill for the shooter as well. Noon's third law also explains why troll logic doesn't really work. Have you ever seen things like this of, oh, why couldn't we do something like this? It's because the Noon's third law tells us that wouldn't work. See, the magnet here would attract the metal plate forward, but according to Newton's third law, the metal plate also attracts the magnet backwards. So both of these effects cancel each other out. And because they're equal forces and they're connected to each other, then it will end up basically keeping the object in equilibrium. All right, so here's the first question. Pause the video, working this off, and we'll go over in a second. All right, so here we have a man pushes a stroller, and they want to know what's the force on the stroller by the man compared to the man by the stroller. Again, the wording is just so weird, and it takes a few times to read it. It's the same. The only time it will ever be something different, like smaller or larger, if instead of asking about the force it experiences, it asks about the acceleration. So do pay attention to that. Make sure they're mentioning force, but if it says acceleration, then ignore the whole the same. Here's the next question. Pause the video, work on itself. We'll go over in a second. All right. So once again, we have two carts. They're being felt by a spring. They say the 1 kilogram cart feels 1 newtons of force. Well, because of Newton's third law, if this feels a 1 newton force to the left, this has to feel 1 newton force to the right. So the answer is A. 14. Pause the video, work itself, and we'll go over in a second. All right. So what we have here is again a setup. Now this is kind of what I mean by where it gets really tricky. So they throw in this stuff of, oh, the Earth is 81 times the mass of the moon, and you'd expect maybe one has a greater effect. But this doesn't matter. What matters is that the forces are always the same. If the Earth exerts a force of F on the moon, then the force of the moon on the Earth is F. The same force. Doesn't matter about their size, the forces are the same. Here's the next video. Pause the video, work itself. We'll go over in a second. All right. So now here we're getting into some other ways that they can ask a Newton's third law question without it being just the same. Here we see a cannonball being shot from a cannon. They give us the masses of the cannon and the cannonball, and they want to know about the acceleration on the cannon. So if we write down everything that's given, we have of the cannon, we have its mass, which is 100 kilograms. We don't know the acceleration, that's what we're looking for. And the only equation that relates these is something about dealing with force. Now for the cannonball, if we write down everything we're given here, we're given that its mass is 20, its acceleration is unknown, but we know its force is 100 newtons. Well, because of Newton's third law, if the ball experiences a force of 100 newtons, then the cannon feels a force of 100 newtons. These two numbers have to be the same. Now I can see what I have to do. I have to do F net equals ma, use the force that the ball feels, and therefore the cannon, use its mass, and I get that the acceleration is 1 meters per second squared. And that's it. That's probably the hardest Newton's third law question that you'll see. So you do want to kind of keep an eye out for that. Again, you can kind of get away with a lot of this stuff by just, paying attention to your units. Again, you want to kind of have F net equals ma drilled into your mind to the point where, again, that's your very first equation to look at. So when you see mass, acceleration, and a force in a question, your mind should immediately go to F net equals ma and trying to figure out where numbers are going to go. Now, You may not want to look too deep into the question. You see a force there, and there's only one single force that you need in order to calculate. There's a really good chance that that is the force you're going to be using. Now, if they give you two forces, then you might have to play around with it. But for the most part, remember, a lot of these questions should not be done in two steps. Most of them are going to be done in one step. So keep that in mind that the questions are typically much easier than you may think. And especially in this part, a lot of the questions are deceptively simple. If you have any questions, feel free to let me know. Make sure you're filling out the note packet. Message me on Remind if you have any questions, and feel free to join the extra out. Good luck and have a great day.